features, like flash, and has a temperature sensor. And then we can use that MSP430 to control sensors and peripherals. So here's some of the functional blocks here. So I'll talk about the rectifier, the demodulator, and the power management block. So here's the L match talked about in front. So, the impedance, the output impedance of a dipole is about 70 ohms. So you can kind of measure that, measure your antenna with a network analyzer to figure out what it is, and then tune this guy up to have the right input impedance that, conjugate matches 75 ohms. So you can see here, you have this AC RF waveform here, and you slowly power up. This is part of our demodulator circuit, charging up, turning on. And then you can see that these AM modulated breaks here, so we're turning those into bits by threshold. So a question I oftentimes get is, what's the input impedance of your rectifier? Now, I always just glaze over, and I've been promising to have a tutorial on how to measure that, but it's just a hard problem. Because it's really dependent on a lot of things. It's dependent on your load. It's dependent on your power level. So this is a three-dimensional graph from the high power work I've been doing, but it was just really nice to kind of explain the problem space. So here's the input power. This is in watts, but the problem space is still the same. Here's the regulated load voltage. We have a dummy load here, and this is the efficiency. So you can see that at different power levels, you have different efficiencies. If you have different loads on the outside, you have different efficiencies. So you have to kind of navigate this curve right here and try and get the right load, which basically means you're not just worrying about the input impedance of your rectifier, you're worrying about the output impedance of your rectifier. There's this big space, and you have to kind of get it right for it to work well. And we cheat a lot on the WISP. Let's see what we got. So here's a typical input power level for the WISP. So input in milliwatts and efficiency, and you can see that, here's our low end sensitivity, and we rectify this is at 1.9 volts. So what does that kind of mean in the power management scheme? So you spend some time, you basically charge up. So we have the supervisor that tells the MSP430, oh, you've hit this threshold, right? And now the MSP430 runs at 1.8 volts. Okay, so now you have this delta here. What time you've turned on, normally you're in your LPM4 state, so you're asleep, not doing anything, trying to use as little power as possible. So that allows you to store energy on your output capacitor. Okay, and then you get the signal to wake up, and you're basically madly trying to do computations before you brown out. So that's like this time. You wake up here, and then you basically have till about 1.8 volts, maybe a little bit less depending on MSP430, to execute your code, get all this stuff done, and then go back to sleep. So then you see this thing where we're kind of bouncing in this realm between 1.9, 1.8 volts. You can change your thresholds a little bit. So this kind of in some ways solved our output impedance problem. That okay, we're just going to say that we're always here at like 1.9 volts. That's it. And okay, and what's my current? Okay, my current is my MSP430 at sleep. Everything shut down at sleep. So now I've defined my voltage. I defined my current. Okay, just tune it up for the minimum input voltage or input power to get to this voltage, right? So I'm not optimizing it. You could think of a strategy where you have this dynamic impedance control module, so that no matter what the input impedance is, you're mathematically getting the maximum amount of power, but we just kind of cheat and say, okay, that's what it's going to be. And it works pretty well. So the demodulator. So here's a typical waveform. I think this is actually Gen 1, but it's equivalent for Gen 2. So here we see these little AM modulated spikes. So here's I think this is zeros, and here's a 1, right? And we need to change it into, we basically need to threshold this and level shift this. So here's a circuit that we have. Dan Yeager, kind of after many iterations, we finally came along this one. And basically, what you can imagine is after you rectify, you're getting these current pulses out, right? Voltage, there's such a large capacitor that you're not seeing a huge voltage swing. So as you put these current spikes, current pulses through your diode, you see this diode drop current. So now you can use your comparator to see this diode drop current across this diode. And then you just have a level shifter that translates this from your harvested randomly changing voltage levels over to the 1.8 voltage world. So again, the MSP430 really isn't this isn't changing anything into bits really. It's just thresholded basically serial data, and now the MSP430's job is to go and try its hardest to in bits ambiguate if these are ones or zeros. there's a lot of work on that side that Dan did. Right. So we talked about some what this duty cycle would be, right? So you spend most of your time off sleeping, charging up. So here's an exaggerated form of that, right? So the threshold was just set to 3 volts. So we spend a lot of time here. We've gone to sleep, spent a lot of time charging up. Oh, we finally got enough power to do something. Our supervisor went off. And now we crash, or now we not crash, but we use up as much, we use this up as fast as possible, do some communication. Here we see, these are actually 2 graphs right on top of each other here. So the pink is transmitted, or received data, and the blue is transmitted data. So we're receiving data and we transmit data here. So we see that we got these queries, we missed all these queries, and then we transmitted here. So, we can see that inherently we're duty cycled. The power management layer, the supervisors, are doing your duty cycle for you. So this is, this is when we're working, and again, we're sleeping most of this time. This is a little bit more typical about what you'd actually see, right? Because we're not allowing these big voltage swings all the way up to 3 volts. So basically, we're on here. We're doing some transmitting packets, right? And then we go back to sleep. And so we can see that here's the duty cycle. Here's what is actually transmitted to us. This is what we receive, and this is when we're asked to respond. So we're not responding to every single one. And basically, our rectified voltage stays at 1.9 volts. Otherwise, we'd use it up, right? It's never going to get higher, no matter how far away you are. Again, I guess the big trick is, depending on how close you are, then you have a larger duty cycle. Like, you need more power in, you have more power to use, and you're on transmitting. When you get further away, you have to wait longer and longer. So let's see. So here's just an example of what our harvester is doing here. So this is input power, this is voltage, and this is power, right? So if we just clip this right here at 1.9 volts and say, okay, up to here, the only thing we have here is the quiescent current draw of our WISP, so 3 microamps or something. MSP430 is like 0.1 microamps. So now we can pull, you can see how much rectified voltage we have. If we kept that rectified voltage constant, then we can see how much excessive power we're getting. So this graph basically shows you, this is about what our turn on voltage is, and then this translates later on to duty cycle. What's kind of interesting is that your power in, as defined, the point where you can turn on is your rectified voltage versus your loss. So when my power in equals my power loss, that's the point I can turn on. So it's pretty easy to kind of figure out where your turn on point's going to be. I guess I threw this slide in just to show like a common measurement technique to figure out how much something actually costs you to do. So this is a read this is a packet and this is a response. And typically what you're doing is if you look on a scope trace, you can just look at your delta on your capacitor to figure out how much things cost. And so there's a lot of debugging that goes around with how much did an ADC read cost, how much did an accelerometer read cost. So this is one method. You can't really do it online. You have to have the scope probes up to measure it. But this is one of the more reliable techniques I found. And then how we're communicating data. So we're using the Gen 2 EPC protocol. And just like Josh had shown in the beginning when we had the WISP with the 2 IDs, right, we're basically we're using the ID space to transmit data. So we're doing the same thing here. We're just overloading the packets using maybe the last 8 bits or so for data and transmitting that back. Of course, it's variable since we have our thing. It just depends how many tags you have in the space. And the other more maybe more responsible way of doing it is using the read command, where the read command asks you to actually go in some piece of memory. This just takes more energy, and I think Michael's going to talk about this later. I think Josh showed this graph quickly before. This is kind of what you would expect to see. So, and the trends are as you go further and further away, the response starts dropping. Well, this makes sense. The further away I go, I have less power, so I can't respond as often. As we start browning out, we get the packet error rate goes way up. So that was a little surprising that the packet error rate was so bad here. I think we made some improvements, but this is, what you can kind of expect. All right, so let me try a demo here. So I think most people have seen accelerometer demo, but I think it's pretty good stuff. Right. Okay. So here, it's kind of washed out, but we